Welcome to the next section of our lecture, where we are going to talk about an interesting topic known as the number systems. And, I feel that a lot of students, when they learn this, and you do learn it in high school, uh, that a lot of us take this for granted because the number systems categorize different types of sets, just as we had done. Now, the way we categorize sets is basically based on how we count, right? We can classify all sets as being either finite or non-finite. And of the finite sets, we can talk about all sets that have no elements in them, all sets that have one element in them, and so on and so forth, right? That is, the collection of all sets of size whatever. We can always relate one collection of sets to another by finding a mapping between them, just by simply the size of their sets. So in order to, we can think of constructing a taxonomy or a classification systems of different types of sets just strictly based on their counts, which means if we're doing this by counts, that simply means that we can actually come up with a classification of different numbers, or put differently, we can actually define, think of it the opposite way. We can actually define numbers as just being nothing more than categories of types of collections of things. So here, in terms of different sets, they're finite or non-finite, and as we mentioned, there's really two different types of non-finite. There's countable, and then there's uncountable, and then there's even more types in the uncountable. That's a little outside the realm of our discussion here, so we'll just leave it as this nice categorization. So all sets can be classified as being under either 0, 1, 2, however many fixed elements are in there, and non-finite sets can be classified as being either countable or non-countable. Now, coming back around, let's first talk about the finite sets. And these are really what we like to call the countable sets. So how can we classify numbers, or how can we construct numbers? If you think about it, this is what mathematics is really all about. It's the philosophical quest into what is a number, and why do I care about it? And how do I define it? And how is it related to other numbers, and etc. So we can actually answer these questions using set theory based on the size of sets. So when it comes to the size of a set, right, we talk about them in terms of the cardinality. And our first basic idea of a number is a count, right? So the basic set of numbers that we can sort of start to think of are what we like to call the natural numbers. And the natural numbers, which is denoted by this funny looking symbol here, is the set of numbers that represent counts of finite sets. And this set, as we mentioned, this itself is a non-finite set, and usually I can never draw this symbol. I have it in the notes. This symbol is what's called alph null. I believe this is in the Hebrew alphabet, if I'm not mistaken. And all it just all it represents is just a designation for the size of the natural number, since we don't really know what that size is. Yes, we could say infinity, but that's really going to cause a lot of confusion here in a few moments. Now, here's some really trippy stuff that we're going to be talking about. The question is, all right, we have the natural numbers, but what about, let's say, the even numbers? So let's take the collection of even numbers, 0, 2, 4, 6, etc. The question I have for everybody, if I can draw this in the font, what is the size of the even numbers? Let's think about this. Intuition might tell us that the size of the even numbers has to be less than the natural numbers, right? I mean, we took numbers out of that set. Think about it. The number 1 is not in here. The number 3 is not in here, but all of these numbers are in here. Put differently, the E here is a proper subset of the N. And so we might initially think that the size of the even numbers has to be less than the size of the natural numbers. I mean, that's a very intuitive thing to think about. For example, if I told you, here's a set 1, 2, and 3. Here's another set. Take out the number 2 and leave just 1 and 3. We very clearly see that this is less than this. So our intuition is telling us that the even numbers needs to have less stuff in it than the natural numbers. Actually, no. And I'm going to prove to you why. Remember what we said. We said that if we can find a mapping between the one set and another set, I have effectively shown that the two sets have the same number of elements. Now, let's suppose we map 0 to 0, 1 to 2, 2 to 4, 3 to 6, 4 to 8, and so on and so forth. That is, I'm going to create a mapping between all of the natural numbers. So for all n in the natural numbers, I'm going to define an f of n as being 2 times the number n. And what do I get as a result of this function? What is the range? Well, this function goes from the natural numbers to the even numbers. Question, is this function bijective? Well, let's see. First, we need to prove surjectivity. Here's how we do it for this case. Let x be even. That is, x is a member of the even numbers. So x belongs in the range here. What I need to show is that there exists a number that I can pass through this function, which will give me my definition of an even number. I can write x as 2 times some number. But n here is any number that's in the natural numbers. And so therefore, if you give me an x, by definition, I'm guaranteed to be able to find an n that I can pass through there. If you don't believe me, and therefore, I was able to find an n in the natural numbers, assuming that x was even. Therefore, this is a surjective function, because if you give me a number in the domain, I was able to give you a number that's in the codomain, I'm able to give you a number that's in the domain, which maps to it. The mapping in this case is being defined as an explicit rule, which doesn't always happen, but in this case it does. What about injectivity? Is this function injective? Let's see. Let's let x1 and x2 be even numbers. By the same reasoning as before, by definition, because they're even numbers, there needs to exist a k1 and a k2 in the natural numbers, such that x1 is equal to 2 times k1, and x2 is equal to 2 times k2. Remember what we said about injectivity. It's injective if we are given two, if I have the two x's equal to each other, that means the two inputs into the function need to also be equal to each other. As it turns out, this is f of k1, and this is f of k2. So here, this is saying f of k1, assume that f of k1 is equal to f of k2. Well, according to our rule, this is 2 times k1 equals 2 times k2. Divide both sides by 2, and we have shown that k1 equals k2. So what have we shown? We showed that when you give me any two numbers or in the codomain which are equal to each other, when I find the function that I pass a k through to get that number, by necessity, the k's need to be equal to each other. Therefore, the function is injective. And because it is surjective and injective, the function f of n is equal to 2n is bijective. What did we prove here? We proved, therefore, that the size of the natural numbers needs to be equal to the size of the even numbers. Mind blown. Think about that. The even numbers do not have the numbers in the natural numbers. They don't have the number 1, 3, 5, and yet they're the same size set. Very, very strange stuff. And as we will continue on, we're going to see some even more strange stuff. Truth of the matter is, when we get to talking about infinity, and this, as you can imagine, is what drove that mathematician Cantor insane, because how can one set be which has the same elements as the other set, but the other set is missing the elements from the first set, and yet they're the same size? That is an incredible realization. Just wait until we get to some more of this topic material.